Welcome back to the deep dive. Today we are jumping into something big, a major paradigm shift in how we think about quality and technology. And our source material really doesn't pull any punches. It puts forward this pretty dramatic thesis, and it says it with, well, zero ambiguity. Testing is dead. Long live validation.
It's definitely designed to be provocative, but it's also true. The old methods we've always used for quality control, in traditional software.
The linear, predictable stuff.
Exactly. The step-by-step process, it just completely fails when it runs up against the non-deterministic nature of AI. I mean, testing comes from a world where input A always gives you output B. In
Mhm.
the AI world, input A might give you output B or B prime or maybe even C, and you need confidence in all of those.
Okay, so let's really unpack this. The sources we've got, this AI validation blueprint, it suggests we're not just tweaking a step in the process. We are fundamentally rewriting the engineering playbook.
We are. And that's our mission in this deep dive. We need to internalize this new playbook. It's about moving away from testing as this, separate, expensive thing you do at the very end.
From an autopsy to what? Preventative medicine.
That's a great way to put it. It's about continuous validation, building robust guarantees right into the generative process itself.
So let's visualize that transition for you.
Yeah.
If you think about the old traditional paradigm,
Yeah.
it was so costly
Mm.
and linear. You'd have this huge block of
Well,
construction,
that's of it.
right? Then a testing phase, then a fixing phase, and then, you'd probably have to retest the whole thing all over again. Testing was always that bottleneck at the end.
And this AI augmented paradigm, it just flips the economics on its head. It's an iterative, really efficient cycle. Generate, then validate, then iterate.
So validation moves to the very front of the line.
It does. And because of that, you catch errors almost immediately.
Mhm.
It just dramatically lowers the cost of each iteration, which is how you get that rapid pace everyone wants from AI development.
So the whole mantra shifts from test last to validate first. But I'm wondering, if the AI is generating something new every single time, how can a test act as a constraint? How is it not just an inspection at the end?
That's because you have to redefine what a test is. A test case isn't just an input-output check anymore. It becomes an executable specification for what quality actually means. The workflow looks totally different. It's
Mhm.
define your test cases first, then you trigger the AI generation, then you run an immediate validation, and if that fails, you refine, you don't move on.
Okay. And what are the key principles that make that shift possible?
There are three, and they're really non-negotiable. First, you have to define success up front. Before the AI generates a single pixel, you have to know what correct or acceptable looks like in a computable way. Second, you use that criteria as an active constraint to steer the AI's generation. It's guidance, not just a stamp of approval.
And the third one sounds particularly important: hallucination anchoring.
Oh, it's incredibly dangerous if you ignore it. Hallucination anchoring it's the risk you run when you build on top of a flawed first output. Imagine a Gen AI for legal research. It spits out one bad citation. That's the anchor.
And then everything else builds on that falsehood.
Exactly. The error just compounds. It becomes catastrophic. Early validation stops that. It says, hey, the foundation is shaky. Stop building. Go back.
That makes perfect sense. But
Yeah.
what about things that are more subjective when we're talking about AI generating images or music?
Yeah.
That's where human judgment comes in. How do you get past just, testing by eyes?
And that leads us straight to rule number one, tame subjectivity with automated proxies. Because you're right, human assessment just doesn't scale. So the goal is to translate those subjective human checks into objective automated metrics.
So you're finding a computable proxy
Yeah,
that correlates with what a human would think.
precisely.
Can you give us a few concrete examples? Because I think this is where a lot of people get tripped up.
Absolutely. Let's start with image generation. A human might check if the image matches the prompt, right? Or if it's original. We can automate that with a proxy called the CLIP score.
And that measures the alignment between the text and the image.
Exactly. It's asking, is what the AI made actually related to what I asked for?
Okay, and what about the quality part? The originality?
For that, we use something called Fresh Eliving Exception Distance, or FID. FID is so important. It compares the distribution of features in your generated images against the features in a set of real-world images.
So a high FID score is bad. It means the generated stuff looks fake or repetitive.
You've got it. So by automating those checks, we're translating that subjective feeling of does this look good into a hard number, a statistical distance.
That's really clever. So what about something dynamic like video or music?
Same logic. For video, a human wants to see smooth motion, right? Temporal consistency.
Things not flickering in and out of existence.
Right. So the automated proxies become things like frame difference analysis and motion vector analysis. For music, instead of asking if it has emotional impact, we can check things like note transition probabilities or if it follows basic music theory rules. It ensures structural sanity, even if it can't, judge genius.
So that handles the subjective side. But these AI systems are still built on code, lots of complex code. Which brings us to rule number 2. Fortify the foundation with code-level guarantees.
And this is where we have to adapt our idea of a unit test. In model math, 1.0 doesn't always exactly equal 1.0 because of floating point calculations.
Right, the classic GPU imprecision.
So we use approximate equality. Instead of an exact match, we test if the result is within a tiny tolerance. It stops so many false failures.
We're basically saying close enough is good enough for the underlying math.
For the math, yes. And to make any of this testing possible when there's randomness involved, we have to use deterministic seeding. You'll see code like torch.manualseed. That ensures that even though the model uses randomness, that randomness is reproducible during your tests.
That makes sense for testing, but I have to ask, doesn't forcing it to be predictable kind of defeat the purpose? Aren't you testing an artificial version of the model?
That's a great question. You're not trying to eliminate the randomness forever. You're just compartmentalizing it for the test. You make the test environment deterministic so that if a test fails, you know it's because the code changed, not because of a random fluke. You still test the real non-deterministic behavior later on, but you know your foundation is solid.
Okay, that clears that up. But even then, we're still just testing specific examples an engineer came up with. We're bound to miss unexpected edge cases.
We absolutely are. And that is why the second part of this rule is so vital. We have to use property-based testing. This approach completely flips the script. You stop testing specific inputs. Instead, you define general properties that should always be true.
So instead of saying, if I input 5, the output is 10, you say something like, the output must always be a positive number. Or, the output can never be longer than the input.
Exactly. And then you use a framework. The blueprint mentions one called hypothesis to automatically generate thousands of inputs. Weird inputs, malformed inputs, things you'd never think of. The framework's only job is to try and find one single example that breaks your rule. It hunts for the edge cases for you.
That sounds like an amazing security tool, which is a perfect lead-in to rule number 3, prepare for the unexpected. Because with AI in the real world, the unexpected is just normal.
So you have to stress it. We perform stress testing. We start with input stress. What happens when you feed it a gigabyte of text or just total garbage data, or data that's completely out of its training distribution.
Train on cats, test on pictures of galaxies.
Basically, yeah. And then you have to stress the infrastructure. That's load stress. What happens when 10,000 people hit your API at the exact same time?
Does the whole thing fall over?
You need to know that. And finally, there's duration stress. Some of the nastiest bugs, like memory leaks or model degradation, they only show up after the system has been running for days or weeks straight.
It's almost comforting to know we still have to worry about memory leaks. But beyond stability, AI has its own unique security problems.
It does. And that's where adversarial testing comes in. You have to proactively try to break your own system. Test for prompt injection, for refusal bypass. The blueprint recommends using tools like the Adversarial Robustness Toolbox, or ART.
What does that look like in practice? An actual test?
Well, you might write a specific test that feeds the model a malicious prompt, one designed to make it ignore its safety rules. And then the test just asserts that the output doesn't contain, say, forbidden information. You're basically playing the role of the attacker to build a better defense.
Okay, so that leads us to the final layer of defense, rule number 4, which is demanding mathematical proof. This sounds intense. When is this necessary?
It's for when failure is simply not an option. Think safety critical systems. Autonomous vehicles, medical diagnosis, grid control systems. In those cases, 99.99% certainty isn't good enough. That 0.01% could be catastrophic. Formal verification is about getting mathematical guarantees.
But isn't that a step backwards? Formal methods are from the old world of deterministic software. How can you demand mathematical proof from something that's inherently probabilistic?
That's the key distinction. You're not formally verifying that the AI will give the best answer. You're formally verifying that its answer will always stay within predefined safe bounds. You're proving properties across the entire theoretical input space.
So you can prove that no matter what the input, the output won't violate some hard safety constraint.
Exactly. You can prove a self-driving car's steering angle will never exceed a physical limit. Or that if a sensor has a little bit of noise, the system's output won't just fly off the rails. It's about putting a mathematical fence around the probabilistic behavior.
Okay, so these 4 rules give us a solid foundation for the components.
Yeah,
But an AI system is more than just the model, right? It's the whole pipeline.
it is. Which is why quality assurance has to cover the entire flow. From the raw data coming in to pre-processing to the model inference and all the way to the business logic that uses the output. You have to test the seams between the components.
And when we talk about performance for that whole system, it's not just about speed, is it?
Not at all. We have to measure what the user actually feels. The most important metric is latency, and not just the average, but the P95 and P99.
The worst case experience.
Right. That P99 user, the 1 in 100 who has a terrible experience, that's often the person who cancels their subscription. So you have to measure and minimize that. Then, of course, you track throughput and resource utilization to manage your cost.
Which brings us to the elephant in the room, the 100% coverage fallacy. If the input space is infinite and the model is non-deterministic, you can't test everything. So where do you even focus?
You shift your goal from 100% coverage to meaningful coverage, and you look at it across 3 dimensions. First is input space coverage. Does your test suite reflect the reality of your production data, including the weird edge cases?
Second,
Architectural coverage. This is deeper. Are your tests actually activating different parts of the model, different neuron paths, different attention heads? You want to make sure you're exercising the whole machine.
and the third is the output.
The output space coverage. You have to catalog your known failure modes and specifically test for them.
And all of this work leads to the final blueprint for continuous validation, the MLOps workflow. Quality control doesn't stop at deployment.
It never stops. Before you deploy, you have data validation tools checking for data drift. Then your component tests. At deployment, you use safer methods like a canary deploy, where you roll out to a tiny fraction of users first.
Or shadow mode.
Or shadow mode, running the new model silently alongside the old one to compare results without any user impact.
And then once it's live, it's all about continuous monitoring.
All about it. Using tools like Prometheus and Grafana to watch for performance drops or data drift in real time. It's a continuous feedback loop.
So if we just quickly recap this new playbook for everyone listening, it's validate first, generate second. It's using automated proxies to handle subjectivity.
It's testing properties, not just examples, fortifying your code, and validating the entire system continuously.
That really is a complete shift in mindset.
It is. And if we look even further ahead, the next frontier is really autonomy.
You mean AI testing AI?
That's the next logical step. Using LLMs to generate new test cases, to triage failures, maybe even to suggest the fixes themselves. And beyond that, we're moving toward causal testing.
Moving beyond just correlation to understand why something failed.
Exactly. You're testing interventions. If I think A caused B, what happens if I take A away?
That feels like a much deeper level of understanding the system.
And the last piece is explainability-driven testing. Using tools like Alibi to not just check the model's output, but to validate the quality of its explanation for that output. Because for big decisions, the why is just as important as the what.
This blueprint really lays out a path for building confidence in these incredibly complex probabilistic systems. You should now have a really clear view of how the most advanced teams are thinking about quality in the age of AI.
Which brings us to our final provocative thought for you to take away. If we all agree that 100% test coverage is impossible for AI, how do we, as an industry, define safe enough? And who, at the end of the day, bears a liability when a system that was mathematically verified fails anyway because of some wild, unprecedented edge case out there in the messy, real world?
Something to think about as you start building this new validation playbook. That's all the time we have for this deep dive. We'll see you next time.